Okay, welcome to lesson 4 in Ochem. Now, the reason for the first 3 lessons was to focus on the configuration around a stereochemical carbon. And the reason for this is because we're going to move very quickly into the dominant reaction mechanisms that are important in Ochem and that we focused on actually months and months of experiments that we did in the laboratory. The next component that we need to cover here is to review the principles of geometry. Around central carbons. Because this is going to be super important in the mechanisms as we go through SN1, SN2, E1, E2, and then when we also deal with addition reactions. All of these reaction mechanisms, and in a lot of cases, more than one mechanism was prevalent in a particular experiment that we did over the since last August. So I'm going to remind you that the way that we find geometry is by establishing the hybridization around a central carbon, and then from there we go directly to the shape, and then I'm also going to talk about groups of electrons. So the first thing that we're going to have, that we always do, hopefully this is spelled right, is we determine hybridization. And so what I'm going to do really quickly is establish a chart here. And then I'll review actually as we go through this. So the first geometry that we're going to talk about is a molecule that has sp3 hybridization, and there's going to be some variation to this. The most basic type of sp3 hybridization, though, will be molecules that are tetrahedral. And when we look and see how many groups of electrons there are, there's going to be there's going to be 4 bonded groups around the central carbon. All right, and we'll just go directly to an example. Again, this is stuff that you've already learned, but you may have forgotten. So I'm not going to go real slow here, unfortunately for you. All right, so we'll start with a molecule of methane. This would be like, where all the basic classes start. You can see we've got 4 distinct chemical groups around the central carbon, which also includes 4 sets of bonding electrons. So to do the hybridization, you count the electron groups and you subtract 1. So there's 1 here, 2 here, 3, and 4. This molecule is sp3 hybridized, and it's also tetrahedral. The bond angles are going to be approximately 109.5 degrees. And I expect you guys to be able to recognize, we just came out of configuration, so you should also be able to recognize when we draw the geometry this way, where now we're taking into consideration the 3-dimensional shape, where the hydrogen that has the hatch marks is going back into the plane of the board. The wedge is projected out, and both of these bonds are in the plane. Okay, and whenever we look at a molecule, so for example, before I move to the next one, perhaps we're looking at acetic acid, for example, you should be able to recognize rapidly that this carbon right here that I just put the asterisk by is sp3 hybridized, and it's tetrahedral. All right, and you should be able to walk through a molecule. You should even be able to do that right now, but we're going to go ahead and go through and review these concepts. All right, let me move on to the next one. And for that, we're going to need a different page view. So I'll take you to the next page. The chart to expedite time will have the same configuration as where we started. So hybridization is going to be here. The next types of molecules we're going to talk about still have sp3 hybridization, only these are molecules that are bent or have central atoms that have a geometry surrounding them which is bent. And for these, you're going to have two chemical groups that are bonded, and you're going to have two unshared pairs of electrons. All right, and the classic example here, actually I'm going to just take you right to an organic chemical representation. So maybe we have an ethyl group here and then OH. All right, and so if I expand the structure on this, I'm going to leave the CH3 just the way it is. Okay, and then I'll expand the methylene group here. And then we're going to have the oxygen, and I'm going to show the hydrogen so that it's adequately bent. And then you can see here we have the hydroxyl group coming off. I'm showing the bent aspect of the molecule. All right, and I'll indicate that by the blue double arrow here. So all hydroxyl groups, and these are always going to be on the external part of the molecule or on the terminal end of molecules, right? Because in order to have a hydroxyl, it's going to have to be on the end of a molecule. All right, although if we look at an ether, for example, which you guys have dealt with, you've actually made them in the laboratory. All right, an ether is going to look like this. So the oxygen in this case is going to be internal. All right, and I'll just keep the molecule simple. So this would be diethyl ether, for example. Notice that we still have the bent aspect of the molecule in here. And it still is sp3 hybridized. So how do we get the hybridization? We count the bonding units. We have 1, we have 2, we have 3, and we have 4. So this is sp3, and it's bent. Okay, moving on to the next example. And in this one, we're going to talk about we're still at sp3 hybridization, but now we're going to talk about pyramidal molecules or pyramidal atomic symbols. And here we're going to have one unshared pair of electrons, and we're going to have 3 chemical groups. All right, and the quintessential example is ammonia, where we have one unshared pair of electrons, and then we have 3 chemical groups around it. You can see when we count up, we have 1 bonding unit here, 1 there, 1 here, and then the unshared electrons. So this is sp3, pyramidal, and the bond angles are going to be around 107. The bond angle is a little bit smaller than the tetrahedral, and the reason for that is because of the unshared pair of electrons, which puts repulsive forces projected against the atoms that are bonded to the central atom. An example here might be something like this. I'll put a methyl group here. And then we have the amine functional group. This comes back to other things that we've learned over the course of the year. This is the amine. All right, and it is sp3 hybridized, and it's pyramidal. All right, so and then to put some of this together as we move through this, so this carbon right here is tet, and the nitrogen is pyramidal. So now you have a way of visualizing this molecule in your mind, where these bonds out here are 109.5, and the bonds that go to the two hydrogens here and then the methyl group are 107. Okay, next in line, and this is actually a really important geometry because it comes up over and over and over again in the organic, in the mechanisms. All right, and it's a major factor, for example, in SN1 and E2 SN1 and E1 mechanisms. All right, and so it's a really important geometry. In this one, there's going to be no unshared pairs. And there will be 3 chemical groups. And I'm going to go straight to the organic example here. So I'll use acetone as the example. You should understand at this point that this is a ketone. It has 1, 2, 3 total bonding units. So the hybridization is sp2. Remember, in terms of bonding units, a single bond is a bonding unit, a double bond is a bonding unit, a triple bond is a bonding unit, an unshared pair of electrons is a bonding unit. So this molecule is planar, trigonal planar. It forms a triangle, and you can sort of see that outlined here. If I do it this way, it's triangular and it's planar. And the reason why this is so significant in organic chemistry is because a collisional molecule coming in, I'll just do it this way for now without starting to get complicated yet, can come in from this side, or it can swing around and come in from this side. So anything that's going to collide with a planar molecule has 2 sides to pick from. 2 sides available for collision. Whereas the other geometries that we just spoke about, the availability of the atomic center, the central atom that was in focus, had other atoms that were extending from it. So if another molecule will have collisions with those particular atomic centers, the collision can be hampered based on what is actually attached to that carbon. So that makes this geometry super important, because basically you've got 2 sides that are completely open to collisions by other external molecules. All right, now we have also another class of sp2 molecules. These are also trigonal planar. They're going to have 1 pair unshared electrons on them, and there will be 2 chemical groups. All right, and the classic example here from inorganic chemistry will be SO2, and the structure is going to look like this. And you can see that it has a, okay, so remember, as we fly through this, that the geometry is based on the chemical groups that are bonded to the central atom and not on the electronic organization itself. So you can see that in this kind of molecule that there are only 2 chemical groups that are bonded to the central atom. So this particular type of sp2 geometry is also bent. The thing is, the bond angle is around 120 degrees versus being something that's closer to water, which is like around 104.5. Right. Nevertheless, these molecules are still bent. All right. Now, moving on to the last possibility will be the situation where we have linear molecules, and these are always going to be sp hybridized. These are linear. All right, and I'm going to go right to, and being linear, the bond angle is going to be 180 degrees. All right, and these can either have no electron pairs with two bonding groups or two bonding atoms, or there can be electron pairs. All right, and I'll give you two examples. So for let's see, for the first one, if we look at something like out of lower level chemistries, we could have this molecule, and you can see that if we look at the central atom here, if we take the carbon, all right, and we do the hybridization, here's one chemical group, here's the second chemical group. So this is sp hybridized, it's also linear. However, if we look at the nitrogen instead, you can see that it has an unshared pair of electrons and then one bonding unit. So it still only has a total of two bonding units. We subtract one, this is still sp and linear. In organic chemistry, the simplest example that comes to mind right now while I'm doing this is acetonitrile, which has this overall chemical structure to it. And if we focus in on the carbon that is triple bonded here, this is sp, right? Because you have one bonding unit here, and then you literally have one bonding unit over here. So this is sp hybridized, it's linear around that carbon. All right, the nitrogen is also sp hybridized because we have an unshared pair here, which counts as a bonding unit. We have the triple bond, which counts as a bonding unit. So this is sp, it's also linear. And then applying what we've learned, right, this carbon right here is sp3, and it's tetrahedral. So now when you look at this molecule, you can close your eyes and actually, visualize what the three-dimensional structure looks like. Okay, so this concludes the video. It's a fast review on hybridization geometry, and then being able to apply those concepts to a molecule.